Hello. In this video, we're going to describe how we implemented a lidar simulation in a Unity game engine. All right. So before we start, let me demonstrate how this lidar actually works here. Okay. So if I start, the lidar generates all these rings, and it scans the surrounding area. Okay. So if I move this lidar, so for example, in the X direction, like so, as you can see, the point cloud changes as I change the position of the lidar. If I bring it up and down, you can see that point cloud changes. Okay, I can even change the orientation, like so. The point clouds update in real time. All right. So that was the default lidar that we modeled here. It's called Velodyne Puck, but there are several other lidars that are actually implemented here. All you have to do is change the name. For example, if you go to the code here, and you can select many different lidars here. Right. By the way, all these codes will be available in the GitHub, and I will describe these the location of this repository in the description below. All right, so let me pick up another lidar here. Let's say Oster lidar, 128 rings with a 1024 beams per ring. If I just copy the name down here, if I start it, as you can see, we have a different lidar here. The previous one had 16 rings. Now we have 128 rings, and you're gonna see a lot more beams here. So if I select the lidar as I've done before, if we move up and down, the point cloud scanning will change, right? We can also change the orientation, and the point clouds responds in real time. All right. So that is the general description of our lidar. And let me show you one last thing here before I jump into the code and the math behind how we created lidar. I created a spline here, and so the lidar will fly through this street, and it'll scan the area. And while it's scanning, it'll collect the point clouds into this 2D texture down here. And you're going to see the collected point clouds display from the top view. Okay. So now if I start this lidar, now the lidar will fly through this spline, and as it flies through, it changes orientation to scan better, top and bottom also. And as you can see on the left and bottom, it generates all the point clouds, and they are collected into this texture, 2D texture, and displays here. All right. Okay. So that's the lidar simulation that I have here, and it has a lot of different lidar implementation here, like I said before. And it has all the Velodyne and some of the Oster lidars here. All you have to do is to copy the model name, place it in the Unity editor, and you should get that particular lidar. All right, so let's get into how we actually implement this lidar. Okay, so the overview or general idea is to use camera. Okay, some of the lidars here that I show you here is 360 degree lidar, surrounding lidar. Okay, but Unity camera is unidirectional. And so what I did here is that I set the lidar, the camera field of view to be 120 degree, right? And then I take a three picture: front, right, back, left, back, and I stitch them together. So when I stitch them together, what happens is the following: from each picture, when I take in a picture, I use vertex and fragment shader to go out there through the camera, find out if there is a beam that goes through from the camera origin through the pixel to the real world, the outer world. And when it hits the geometry, it'll find the point normal as well as the range value from the camera to where it hits the geometry. Okay. Once it gets that value, using vertex and fragment shader, it'll take that value and generate a 2D texture from it. Instead of populating with color, we store the range as well as point normal onto the texture. We do that for every single pixel down here. Okay. Once we do that, then we further utilize the compute shader to query, okay, based on the UV coordinates of the particular pixel. We can use the UV coordinates to extract out the float 4 value of the range and point normal. We extract that using compute shader. Once we extract that compute shader, we put them into a long array, and then from the array, we convert that array into Cartesian coordinates so that I can point where it is, where it hits, and then I put a point normal there so that I can display it in the Unity. So that's the general idea of how we utilize the vertex and fragment shader and compute shader to simulate the lidar. The reason that we're using all these shaders is because we're utilizing GPUs. That's why we were able to show the point clouds change in real time. It's fast. Okay. All right. Let's jump into the code. All right. So first thing first, let's discuss the shader, the vertex and fragment shader. Those of you who doesn't really have much background in the HLSL or shader lab, you need to have some background to understand this code. There are two shaders here, which one is vertex shader, the other one is fragment shader. Okay, vertex shader collects the position and projection of the position from the camera view and normals, all that stuff. Okay, we collect that from vertex shader and then pass it on to fragment shader. And what it does is that it computes the range, the normalized range value from 0 to 1, and then multiply that to point normal, so that we can encode those into float value 3 xyz float value, and then just one empty space, I put on 1 here. But once we do that, then this shader runs for each pixel and it'll generate this texture here. Once we have that texture, then we use this compute shader. First, utilize the UV coordinates of that pixel, and then we extract out we sample the float 4 value for that pixel, and then we store it into a long array. Then once we have the array value, then from the C# side, what we do is that we for each pixel, for each data point, we convert that into a Cartesian coordinates and display it on the Unity using gizmo draw, on draw gizmos function. Okay, so that is the general idea of how we implemented this lidar. One of the advantage of our lidar here is that because we're using pattern-based lidar implementation, we can use that. We can generate the lidar very quickly. Okay, what I mean by that is that, for example, let's say that we would like to implement this particular lidar, which is Oster lidar, 64 beam, 1024 number of data points per ring. Okay, for that, all you need is horizontal field of view, horizontal beam, number of beams in the horizontal field of view, the vertical number of vertical beams, vertical field of view, that sort of stuff. Once you collect these information, and once you package it like this inside of this code, in this code, you just add another one down here like this, okay, with these information, then our code here will generate the corresponding lidar, okay, automatically. That's because behind the scene, we're doing this simple trigonometry to generate the patterns of lidar, patterns of data points per camera view. So like I said, we have 3 different views of this of the lidar. For each view, you generate this pattern, okay, and then we stitch them together on those three the direction, and that's how we generate this 3D surrounding lidar, 360-degree lidar. Okay, so that's the idea. That's that's the basic idea of how we made all these different lidar implementation automated. Okay, so that is how we implement these different lidars relatively quickly. One more thing that I would like to point out is that, as you have seen, these lidars are very regularly spaced. But using this simple math, you can also generate the lidar that are not so regularly spaced. For example, some of the Oster lidars, those have different beam pattern. For example, let's pick up Oster 32 beam, 512 gradient lidar. If you plug in that in here, and let me turn off the spline, uh, as well as spline implementation here, and then we're using the gradient lidar. So I start it. Now you're gonna see, let me turn this thing 90 degree so we can see it better. Okay, so about 90 degree, right? As you can see, I'm scanning on this ground here, and as you can see, as we close to the center, the density of the beam is high, but as we move away from the center, the beam's getting sparser. You mean the distance between the line ring becomes larger. Okay, this is called gradient lidar, and this is one of those Oster lidar implementation. And using the same mass, we were able to implement this lidar relatively quickly. All right, that's it for this video. Thank you so much.